Hello. In the unit Atomic Structure, in today's class we will discuss Rutherford's atom model. Now let us move on to the most important discovery in physics. This was possible because of an important experiment which is called alpha particle scattering experiment. Now this experiment was designed by Ernest Rutherford. Before we begin discussion on this experiment, let us consider Rutherford's background briefly. Uh, Ernest Rutherford, he was Thomson's student in Cavendish Laboratory in University of Cambridge between 1895 and 1898. Now, from 1898 to 1907, he worked in McGill University in Montreal, Canada. There, he made his initial major discoveries he made in McGill University. Frederick Soddy was his research assistant there, and Rutherford discovered there that his major discoveries were he discovered the radioactive half-life. He discovered the radioactive element radon, and he also differentiated and named this alpha radiations and beta radiations. Okay, because of these major contributions, he got Nobel Prize in Chemistry in 1908. Okay, in 1907, Rutherford came to Manchester University in England. And there, in the figure, you can see Hans Geiger on the left side. Hans Geiger was Rutherford's research assistant in Manchester University. On the right side, you can see Ernest Marsden. Marsden was his PhD student. Okay. Now here, from 1907 onwards, Rutherford was involved in a series of experiments which led to his greatest discovery. Okay, Rutherford's case is exceptional in the sense that his greatest discoveries came after he got a Nobel Prize. In this case, a Nobel Prize in chemistry. Between 1907 and 1909, in the 2-year period, Rutherford and Geiger developed two different techniques for the detection of alpha particles. First one was counting scintillations on a zinc sulfide screen. Scintillation means bright spots. So when alpha particles are incident on a zinc sulfide screen, they get bright spots or scintillations, and these scintillations can be counted. That was one technique. Second one was measuring the electrical discharge in an ionization chamber. They designed an ionization chamber for that, and when an electric discharge is produced, it means that an alpha particle is passed through that chamber. Actually, Hans Geiger developed this second method to design Geiger counter, and later he further designed it along with Muller as Geiger-Muller counter. Short form is GM counter. Okay, so that that measurement technique was originated in this Manchester University lab in this period. Okay, and in 1909, Rutherford and another PhD student, Thomas Royds, showed that alpha particles are ionized helium atoms. Okay, helium atoms where the 2 electrons are removed. In today's terms, we say that alpha particles are helium nucleus, but at that time the idea of nucleus was not there. So ionized helium atoms. So the point is that by 1909, Rutherford and his team were very sure about the structure of alpha particles, and they developed two different techniques for measuring alpha particles. Now, with this background, Rutherford started using beam of high energy alpha particles to probe the structure of the atom. During the period 1908 and 1909, Geiger and Marsden measured how alpha particles are scattered by metallic foils, different metallic foils. Now here we can see an experimental arrangement of their technique. There is a radiation source, the radiation source of alpha particles. They used either radium or radon. Then when alpha particles are passed through a collimator, they get a narrow beam of alpha particles. Here is a metal foil, either gold foil or any other metal foil. Then when alpha particles are scattered, they used a fluorescent screen, a zinc sulfide screen. Okay, the first type of technique, measurement technique is used, that is counting the scintillations on a zinc sulfide screen. So wherever alpha particles hit the zinc sulfide screen, they get scintillations. Okay. Now they first studied small angle scattering. Small angle scattering means if this is the incident beam, okay, if there is no scattering, the beam goes like this. Okay. Now the deviations from the incident beam, if this is the incident direction, the deviation is the scattering angle. So these are small angle scattering. Okay, the scattering angle is of the order of 1 degree, 2 degree, up to let us say 10 degree. So initially they studied this small angle scattering. Then they noted that a few alpha particles were scattered by large angles. Here these are large angle scatterings. Okay, and a very few were even back scattered. Okay, here the scattering angle is very high. This is the incident beam. Okay, up to here let us say 90 degrees. So this is close to 180 degree. So if it just comes back, it's called 180 degree scattering or back scattering. So they noted that very few alpha particles, very few were even back scattered. Okay. You can see Rutherford's response when Geiger and Marsden reported this unusual case of large angle scattering. Okay, this particular statement Rutherford made in 1936 in a lecture in 1936, 1 year prior to his sudden demise. So he was remembering those incidents in 1909. So he was saying that it was quite the most incredible event that has ever happened to me in my life. Okay, it was almost incredible, as if you fired a 15-inch shell at a piece of tissue paper. A shell is like a cannonball. It's a cannonball. A 15-inch shell at a piece of tissue paper, and it came back and hit you. Okay, so this backscattering was a very incredible measurement, a very incredible experimental discovery. So in the next 2 years, in 1909 and from 1909 to 1911, Rutherford systematically tested each aspect of the scattering experiment, okay, with Geiger and Marsden. So this team redid all the different aspects of the experiment. They redid all the measurements, okay, checked all the measurements, and Rutherford tried to explain the results using existing atom models, in particular Thomson's atom model. What if Thomson's atom model was correct? Okay, we know that in Thomson's atom model, the positive charge of the nucleus is uniformly distributed over the sphere of the atom, and electrons are randomly distributed or maybe revolving in this positive sphere. Okay, now if the positive charge is uniformly distributed over the atom, then when the alpha particles are coming, okay, alpha particles are ionized helium atoms. That means they have 2 units of positive charge plus 2e. So when they are coming, they will experience repulsion. Okay, but this force per unit area, okay, the force of repulsion per unit area experienced by the alpha particles will be very small. Why? Because the positive charge of the atom is uniformly distributed over the atomic sphere. So if the force per unit area is very small, what happens? Most of the alpha particles will pass through the atom without any scattering, and some of the alpha particles may undergo at most small angle scattering of the order of 1 degree, 2 degree, etc. So if Thomson's atom model were correct, all the alpha particles should have, most of the alpha particles should have passed without any scattering, and some should undergo a small angle scattering only. There should not be any large angle scattering or back scattering. So this shows that the results, actual results of alpha particle scattering experiment shows that, or showed that Thomson's atom model was not correct. That was the conclusion obtained by Rutherford, Thomson's own student. How did Rutherford explain the large angle scattering? Now, Rutherford found that the large deviation from the path of a massive charged particle like alpha particle. Remember, it's a if it is a ionized helium atom, it has 4 atomic mass unit mass and 2 plus 2 units of charge. Okay, so it has charge and it has a heavy. It's heavy. So such a particle, in order to cause a large deviation from its path, then it can be explained only one way. Okay, most of the mass of the atom and most of its charge must be concentrated in a very small central region. Okay, in a very small central body, and this central region was later called nucleus of the atom. So this idea of nucleus, that means the mass of the charge and it's most of the mass of the charge and its total positive charge must be concentrated instead of uniformly distributed as Thomson proposed. It should be concentrated in a very small region at the center of the atom. Okay, we call it nucleus. So this idea Rutherford obtained by analyzing the experiment, the alpha particles, the results of alpha particle scattering experiment. Rutherford derived a scattering formula. Okay, this was the formula derived by Rutherford. This n theta is the number of alpha particles per unit area reaching the screen at a scattering angle theta. Okay, scattering angle means the angle between the incident beam, the direction of the incident beam, and the direction of the scattered beam. Okay, if scattering angle is theta, then number of alpha particles per unit area reaching the screen, okay, is equal to Ni nt z square e raised to 4 divided by 8 pi epsilon 0 square r square kinetic energy square and sine raised to 4 theta by 2. Ni is the total number of alpha particles incident on the target foil, and small n is the number of target atoms per unit volume in the foil. T is the foil thickness, and Z is the atomic number of the foil atoms. In the original alpha particle scattering experiment, they used gold, whose atomic number is 79. Okay, so that is that. And R is the E is electronic charge, of course, and this is a constant we know. R is the distance of the screen from the target foil. Okay, the distance between the target foil and the zinc sulfide screen. And here the kinetic energy is half mv square, the kinetic energy of alpha particle, the initial kinetic energy of alpha particle. Theta is of course the scattering angle. So this formula, the derivation is not part of our syllabus. If anybody wants to study the derivation, you can refer the appendix by in Arthur Baser. Okay, it's a detailed derivation, and even if you don't study the derivation, you should be familiar with some of the aspects of this this formula. It is directly proportional to the thickness of the foil. So if foil thickness doubles, the number of particles becomes doubles. Okay, number of scattered particles doubles along a particular scattering angle. So it is proportional to foil thickness, then proportional to square of the atomic number. Okay, proportional to 4th power of electronic charge. Okay, then inversely proportional to square of the kinetic energy, or you can also say 4th power of velocity of the alpha particle. Okay, kinetic energy is half mv square, so 4th power of velocity is there, and 4th power of sine of scattering angle. Okay, these parameters, important parameters on which this scattering number of scattered particles, alpha particles, depends. So Rutherford made this derivation in 1911. Okay, in the previous slide also you must have noticed that time May 1911 was the time, was the period at which Rutherford published his paper explaining atomic structure with the idea of a small central nucleus. In the previous slide, I have given a hyperlink to there is a web resource detailing the story behind the discovery of the atomic nucleus. Now, here is the experimental verification of Rutherford's scattering formula. How the number of scattered particles depends on the scattering angle. Okay, from the previous slide, you remember the scattering formula. Number of scattered particles is inversely proportional to fourth power of sine of theta by 2, right? So that dependence, when as theta increases, the number of particles decreases. Okay, you can see that the number of scattered particles is very high towards small angles, okay, towards small angle scattering. That means most of the particles will undergo small angle scattering. Most of the particles are coming here. When you go to 180-degree back scattering, only very few particles will undergo back scattering. So that trend in the scattering is clearly reflected in this formula. Okay. So Rutherford scattering for not only this theta dependence, the other parameters like how it depends upon the foil thickness, then how it depends upon the velocity of the incident velocity and the velocity of the kinetic energy or velocity of the alpha particles, and how it depends upon the atomic number of the target atom. These different aspects were experimentally verified in the 2-year period between 1911 and 1913 by Geiger and Marsden and in Rutherford's lab. So it was found that this formula was essentially correct, and it very well matches with experimental data. Okay, and another important point is this formula, Rutherford's formula, breaks down at backscattering at 180-degree. When backscattering happens, Rutherford scattering formula fails. So during this period from 1911 onwards, once he derived this formula, Rutherford was systematically looking for the scattering or by large angle scattering where his formula fails. Okay, so let us see what happens at the backscattering at the instant of the backscattering. Okay, what happens during backscattering? See, I told you that at the time of backscattering, Rutherford scattering formula fails. Now, Rutherford estimated the size of the nucleus, okay, at the time of by considering the situation at the time of backscattering. During backscattering or 180-degree scattering, there must be head-on collision between the incident alpha particle and the nucleus of the target atom. Okay, in the figure you can see that when the alpha particles are moving slightly away from the nucleus, they may pass without any scattering. Those coming near may undergo large angle scattering. If there is a head-on collision, there is almost a backscattering. Okay, now when the alpha particle is far away from the target atom, it has some kinetic energy. Let us call it kinetic energy alpha. Okay, it is far away. It's coming here. Since the distance is very large, let us say r tends to infinity, the electric potential energy of the system is 0, negligibly small or 0. So what is the total total energy of the system when the alpha particle is very far away? Only the kinetic energy of the alpha particle. Okay. So we have the target nucleus and the alpha particle is coming. Alpha particle has plus 2e charge. Target nucleus has some z times e charge. Both are positive charges. So when the alpha particle comes nearer to the target nucleus and reaches a distance of closest approach, okay, minimum distance, then its kinetic energy reduces to 0 and then it is repelled back, 180-degree scattering. So we can say at the distance of closest approach, let us use the symbol capital R for that, the kinetic energy of the alpha particle is almost 0. So what is the total energy? It should be equal to electric potential energy at R, at a separation R. What is this electric potential energy? 1 by 4 pi epsilon 0 Q1 Q2 by R. Now Q1 is charge of the alpha particle, which is plus 2e. Q2 is charge of the nucleus, which is Z times E, where Z is the atomic number, divided by R. R is the separation distance, okay, distance of closest approach. Now, when the alpha particle was very far away from the nucleus, what is the total? What was the total energy of the system? Kinetic energy of alpha particle, right? And when the alpha particle reaches the distance of closest approach, kinetic energy reduces to 0, but now there is a electric potential energy. When it was very far away, there was no electric potential energy because the distance was very large. Now, equating the total energy at both positions, total energy must be the same in both positions. Initial total energy, which is kinetic energy of alpha particle, equal to final total energy, which is potential energy of the system. Now, we can rearrange that and obtain an expression for distance of closest approach, 1 by 4 pi epsilon 0 2z e square by kinetic energy of alpha particle. Now, this distance of closest approach is an approximate estimate of the size of the nucleus. Okay, it is not exact because alpha particle need not come up to the surface of the atomic nucleus. Okay, particularly when Rutherford was doing all these experiments, only alpha particles from natural radioactive sources were available. There was no particle accelerator at that time, so Rutherford could not accelerate charged particles. Therefore, from the natural sources, radioactive sources, the kinetic energy of alpha particle was of the order of 5 mega electron volt. So at the 5 to 10 mega electron volt maybe. So these alpha particles might not be able to reach the surface of the nucleus. So the distance of closest approach, by the best guess, it should be larger than the radius of the nucleus, but it gives you an upper limit of the size of the nucleus or radius of the nucleus. So that is the idea about the distance of closest approach. In 1919, okay, 1919, Rutherford was able to show a breakdown in his scattering formula for alpha particles of kinetic energy 7.7 MeV scattered at large angles for aluminum nuclei, okay, whose atomic number is 13. So let us calculate the distance of closest approach with this data. From the previous calculation, this is the expression 1 by 4 pi epsilon 0 2z e square by kinetic energy of alpha particle. Now in this expression, a particular combination e square by 4 pi epsilon 0, okay, this e square by 4 pi epsilon 0, if you rearrange that, z is only a number, it has no unit. So therefore, if you keep e square by 4 pi epsilon 0 on one side and take this kinetic energy alpha to the left side, kinetic energy is energy which has the unit of joule. R is distance of closest approach, it has the unit of meter. It means that e square by 4 pi epsilon 0 should have the unit of joule meter. Now if you convert this into electron volt meter, remember we have done this type of a calculation in the case of HC. H Planck's constant, C speed of light in vacuum. HC is also joule meter unit. We have converted it into electron volt meter, electron volt nanometer actually, 1240 electron volt nanometer. We can also rearrange that in terms of MeV Fermi, right? In the same way, this e square by 4 pi epsilon 0, if you calculate, and I suggest that you do this calculation yourself. You know 1 by 4 pi epsilon 0 is 9 into 10 raised to 9. And the e square value also you know, that will give you joule meter in joule meter. Then you divide with the electronic charge, okay, then one electronic charge get cancelled. So this calculation is very easy, and what you get is a neat number 1.44 electron volt nanometer. Okay, you know that this electron volt nanometer you can also rewrite as MeV femtometer. So this is very useful. E square by 4 pi epsilon 0 appears in many formula in particularly when we discuss Bohr model, you will see that this combination appears in many formula. It's a very important constant, and we will also see one more constant related to that combination. Okay, anyway, this one, remember this value and you do this calculation and verify that. So what I am going to do is here, instead of e square by 4 pi epsilon 0, I can substitute 1.44, and I am choosing this particular combination with this particular units, MeV Fermi. Why? Because in the denominator you have kinetic energy of alpha particle, which is 7.7 MeV, right here. So MeV will cancel. That's why I'm doing that. And 2 is Yeah, it is the atomic number of alpha particle. Z is the atomic number of the target nucleus, which is aluminium. If you do this calculation, you will get 4.86 femtometer. So this is the this was the distance of closest approach Rutherford obtained in 1919 for aluminium nucleus. So it gives an upper limit at the best. It gives an upper limit of the radius of the aluminum nucleus. And see, the current estimate of the size of the aluminum nucleus is 3.6 femtometer. So this is a very good estimate in that sense. So in this way, distance of closest approach is a good estimate of the, particularly when the kinetic energy of the alpha particle is large. It's a good estimate of the size of the nucleus. And so size of the atom is of the order of 10 raised to minus 10 meter, 1 angstrom. And size of the nucleus, by 1919 Rutherford clearly established that size of the nucleus is of the order of 10 raised to minus 15 meter for small nuclei like aluminium. When you go to larger nuclei, size increases, so it can go up to 10 raised to minus 14 meter. So generally it is of the order of 10 raised to minus 15 meter to 10 raised to minus 14 meter. So if you make a comparison between these two, so we can see clearly that size of the atom is 10 raised to 5 times, right? 10 raised to 5 means 1 lakh. 1 lakh times greater than size of the nucleus. How do we make this? We make a visualization or a feeling of this one. Because 10 raised to minus 10, 10 raised to minus 15 are all the same for us, because we don't have any feeling of such small magnitudes. So let us, one way of making an experience of these numbers is you translate these numbers to our dimensions. Okay, let us say this 10 raised to minus 15. We want a comparison between 10 raised to minus 15 meter and 10 raised to minus 10 meter. Let us assume that this 10 raised to minus 15 meter is equal to 1 centimeter. Okay, or 10 raised to minus 15 meter we blow up into 1 centimeter. So let us assume that suppose size of the nucleus is 1 centimeter. Then what will be the size of the atom? It should be 10 raised to 5 times greater, right? So that means if nucleus is of the order of 1 centimeter, atom should be of the order of 10 raised to 5 centimeter. Okay, now what is this 10 raised to 5 centimeter? Let us convert it into meter. It is 10 raised to 3 meter. 10 raised to 3 meter means 1000 meter. 1000 meter means 1 kilometer, right? So if nucleus is some entity with a dimension of 1 centimeter, a radius of 1 centimeter, then the atom as a whole should be an entity with a radius of 1 kilometer. For example, you imagine a very big stadium. Let us say, I think an Olympic stadium, the diameter of, it's not circular, but still approximate diameter of an average radius of an Olympic stadium is about 130 meter. 130 meter radius. So you imagine an Olympic stadium, that's what I think, you check. You consider an Olympic stadium which is some 10 times higher than a typical Olympic stadium, a very big stadium, a stadium whose radius is of the order of 1 kilometer. If an atom is such a stadium, a nucleus is a small fly of dimension 1 centimeter at the center of that stadium. So that is the vast difference between size of an atom and size of the nucleus. And the rest of the atom is simply empty space. Okay, most of the atom is empty space. The entire, almost the entire mass of the atom, except those of electrons, all the positive charge of the atom are concentrated at this very tiny central region. Okay, so the Rutherford was successful. He was the first person successful in estimating the dimension of the nucleus also. With the information he gathered from alpha particle scattering experiment, Rutherford was able to propose his own atom model in 1911. What are the important features? We have already seen the different aspects. Let us consolidate them. Most of the mass of an atom and all of its positive charge must be concentrated in a very small central region called the nucleus. Size of the nucleus is very small compared to the size of the atom. Total negative charge of the electrons is equal to the total positive charge of the nucleus, so that the atom is electrically neutral. The electrons revolve around the nucleus as in a planetary model. Okay, so this is the central region, nucleus, and the electrons are revolving around the nucleus in different orbits. So this was a sort of planetary model of the atom. So this was the model proposed by Rutherford in 1911, and by the time 1919, Rutherford also discovered proton. Okay, that every nucleus must contain this entity, a positive charged entity, proton. That also he discovered by the time 1919. Now, is this model stable? The problem here is this. According to classical electromagnetic theory, any accelerating charged particle radiates energy. This we have seen when we discussed X-ray production, okay, about Bremsstrahlung radiation. Okay, here the Rutherford proposed that electrons are revolving around the nucleus. Then a revolving electron has centripetal acceleration, and hence it should radiate energy. If it radiates energy, its energy should decrease. Okay. Now look at this formula. We can actually write an expression for the total energy of such a, consider for example Rutherford's atom model for hydrogen atom. Okay, so there is a plus E charge at the center. There is an electron with minus E charge revolving around the center nucleus. Then the total energy of the system, you can show that it is equal to minus E square by 8 pi epsilon 0 into R, where R is the radius of the orbit, E is the energy. Now then you can invert this formula and you will get R is equal to minus E square by 8 pi epsilon 0 into E. So what happens when energy E decreases? Okay, when energy E decreases, the radius, the expression for the radius becomes more and more negative. That means the radius of the electron's orbit should decrease. Okay, when energy decreases from this formula. If the radius decreases, what will be the path of the electron? Okay, it should look like this. Let us see. So if this is the nucleus, okay, and if the electron is revolving around the nucleus in a circular orbit, then as it revolves, it should radiate energy, and its energy should decrease, right? Then its radius also should decrease. That means it should move in a spiral path, in a continuously decreasing radius, and finally fall into the nucleus. Okay, this should be the path of the electron. So when it finally falls into the nucleus, what happens? It destroys the atom. Okay, so we know that this doesn't happen because we know that atom is stable, and that's why we are here. Okay, the entire universe is here. It accounts, it's an evidence, direct evidence for the stability of the atom. So somehow Rutherford's model could not explain the stability of the atom, or we can see that it is in contradiction with the classical electromagnetic theory, okay, in terms of the stability of the atom. So this was one problem with Rutherford's atom model. So we have seen that Rutherford's model, Rutherford's alpha particle scattering experiment was a very epoch-making experiment in physics. In the sense that it was the first instance where high energy particles are smashed into target foils, target nuclei, to study the structure of the atom. Okay, this was in 1909. Okay, more than 100 years before, and even 100 years after. This is the major way we study the structure of particles, structure of matter, even now. Okay, you have heard about Large Hadron Collider in CERN, in other particle accelerators. So what we do essentially is we smash the particles together. So high energy particles are smashed together. So we then by analyzing the results, we try to infer information about data about the structure of the if not structure of the atom or structure of the nucleus. We study the structure of the nucleus, we study the structure of fundamental particles, nucleons, okay, and other fundamental particles. We discover newer and newer particles. So in that sense, that alpha particle scattering experiment designed by Rutherford and done by Geiger and Marsden was really an epoch making, a new paradigm in experimental physics. And this experiment allowed Rutherford to prove that Thomson's atom model was not correct. It also allowed him to discover the idea of atomic nucleus and propose a new planetary model of the atom with the size of the nucleus very small compared to the entire size of the atom. So in that sense, Rutherford model was a very major step in physics. But at the same time, like any new theory, it also opened many, raised many open questions. Okay, these are the major questions raised by Rutherford's model. How do the electrons move around the nucleus to form a stable atom? Already we have seen that Rutherford's model is in contradiction with classical electromagnetic theory in terms of the stability of the atom. So how do the electrons move around the nucleus to form a stable atom? How does their motion explain the observed spectral lines? Okay, in the previous class we have discussed the long history of atomic spectra right from 1800 onwards. So the rich history of 100-year history of atomic spectra. So how does their motion, the motion of the electrons around the nucleus, explain the observed spectral lines, okay, of different atoms? If there are only Z protons in the nucleus, what causes the other half of the nuclear mass? Okay, these questions were raised in 1911. Okay. What force keeps the many protons confined to a very small region of size 10 raised to minus 14 meter? You know, protons have positive charge, they undergo electric repulsion. So if they are tightly packed to a very small central region, then there must be some cohesive force, attractive force between them. What is that force? Okay, is it electromagnetic force or some other force? These were the questions raised by Rutherford's atom model. And in the next class, we will see the answer to the first two questions. Okay, these two questions were answered by Niels Bohr. Okay, so in the next class we will discuss Bohr atom model of hydrogen. Thank you.